Before we move on and talk about before we move on and talk about a different type of technique that we're going to be using for integrating and finding some of the areas of these regions, we want to do a brief review on how to graph functions where x is a function of y. We're very used to seeing y as a function of x, but it's also helpful to remember how x can be a function of y because sometimes some of these regions are going to be easier to think of in terms of curves where x is a function of y. So if we're graphing something like x equals y squared, we might start with our usual technique of just plotting a bunch of points. So if I'm thinking about something like y equals 0 here, I find that x equals 0. So I'm going to have this point on my graph. If I were to pick, say, y equals 1, so we have y equals 1 here, then we know that x is 1 squared, which is 1. If I were to pick y equal to 2, x had better be 4. So maybe 4 is somewhere out here. If I were to pick 3 for y, then x had better be 9. Likewise, if I want to pick some negative values for y, so maybe I pick negative 1, then so y is negative 1, x is going to be minus 1 squared. Minus 1 squared is positive 1, so somewhere out here. If I pick minus 2, then x had better be minus 4. And if I pick minus 3 for y, then x had better be 9. So we see that the picture here looks very similar, or maybe not very similar, but it shares some properties with with y equals x squared, and that this is going to look a lot like a parabola. It's just a parabola on its side, however. So again, kind of similar. Maybe it looks like it's rotated, but that's not quite the picture that we want to have in mind here. And we'll take a look at some other graphs to sort of see exactly what's going on as how we get maybe from the graph of y equals x squared to the graph of x equals y squared. For example 7, if we're graphing x equals y cubed, well, again, we might want to pick some different y values here. We're going to again have y equals 0 implies x equals 0. Y equals 1 is going to imply x equals 1. Y equals 2 is going to now imply that x equals 8. So we're all the way over here. And if I pick some negative values, maybe I pick minus 1 for y, then my x value now is going to be minus 1 cubed, which is negative 1. And let's see, if I pick negative 2 for y, then x is going to be all the way out here at minus 8. So I have some function that looks kind of like this. And here we see that this isn't quite a rotation of the graph y equals x cubed. So if this here is x equals y cubed, we remember something about what y equals x cubed looks like. If I were to try to rotate this graph, if I were to rotate it, let's say, by an angle of pi over 2, then I would end up with something that looks like this. If I were to keep rotating it, I would end up, maybe I rotate it by another pi, then I'm going to get the same picture. And in fact, no rotation of the graph y equals x cubed is going to get me to this graph x equals y cubed here. There's something a little bit different going on. So let's sort of see what that exact thing is. So remember kind of what we're doing. If we're looking at the graph of x equals f of y, then we are reversing the usual roles of y equals f of x. Roles of x and y. So what does it mean to reverse the roles of x and y? Well, if I take some point here, maybe the point 3, 0, and I reverse the roles of x and y, then I get the point up here at 0, 3. If I take the point, let's say 1, minus 2, and I reverse the roles of x and y, then I get the point at minus 2, 1, which is somewhere up here. If I take the point, let's pick this guy here. Let's say I've got the point -1 comma -3. I reverse the roles of x and y. I'm going to get the point -3 -1. And maybe something that seems reasonable here is that what's really going on is that all of these points are being reflected across the line y equals x. So I'm taking this point here at -1, -3, and I'm reflecting it to get to -3, -1. This point here at 1, -2 gets reflected to become -2, -1. And this point here at 0, 3 becomes reflected to get the point 3, 0. So when we reverse the roles of x and y, what we find is that we're reflecting something across the line y equals x. So our general procedure for drawing the graph of x equals f of y should be something like, first, think about the graph of y equals f of x, and second, reflect across the line y equals x. So let's do an example of that here with x equals arctangent of y. So step 1 would be draw the graph of, let's do y equals arctan x in purple. So if we are drawing that graph, let's see, that might look something like, what do we know about arctan x? Well, we know that arctan of 0 is 0, so we're going to have the point 0, 0 on our graph. We know that as x goes off to infinity, our y values get closer and closer to positive pi over 2. And we know that as x goes to minus infinity, our y values get closer and closer to minus pi over 2. So the next thing that we want to do then is we want to think about what exactly would it look like to reflect this graph over the line, across the line y equals x. So here's my rough line y equals x. And now in order to draw, let's say, x equals arctan y, so this is my second step here, is actually doing some reflecting. Well, I'll be taking the points that live over here with large x values and y values close to pi over 2, and I'll be reversing that, and I'll be giving them large y values and x values close to pi over 2. So x close to pi over 2 is going to be somewhere over here. Oops. Let's see. So x close to pi over 2 is somewhere here. Reflecting those vertical or those horizontal lines across the line y equals x is going to turn them into vertical lines. So we'll have a vertical line at pi over 2 and a vertical line at minus pi over 2. And as I mentioned earlier, these points with large x values and y values close to pi over 2 become points with large y values and x values close to pi over 2. All right, so let's draw kind of what that looks like. So that's going to look something like this. And the points with very negative x values and y values close to minus pi over 2 become points with very negative y values and x values close to minus pi over 2. So in the end, my function x equals arctan y looks a lot like this red graph here. And if I think maybe a little bit about what x equals arctan y might look like, maybe I could remember that x equals arctan y, if I take tangent of both sides, I get tangent of x on the left, and tangent and arctangent are inverse to each other to an extent. So the right-hand side looks like y, and in fact what I see is that maybe this graph should look something like y equals tangent x, and that's in fact a lot like what I drew here. Now maybe there's a question of why don't I include the other parts of y equals tangent x, and that's because arctangent, in order to be a proper function, can only have one output at a given input. And so the arctangent function here can't spit out y values also up here or down here, which would be necessary in order to get the remaining branches of the tangent function here. So by the fact that arctangent is a function, we need to restrict it and only consider the y values that are between minus pi over 2 and plus pi over 2.